regional contest, and yesterday you took part in this contest in Russia. We have the following schema of ACM ICPC contests. We have about 15 sub-regional contests around Russia and around ex-USSR countries. And the best teams from these sub-regional contests advance to the regional contest in St. Petersburg, NIRC, and the best team from NIRC go to World Finals. And yesterday you took part in sub-regional contest from Saratov State University. For many years I am chief judge of this contest, and that year was not an exclusion. But actually we have very huge team of judges, because in Saratov, you know, we have a long history of participating in ACM ICPC, and many retired participants, champions and so on, are involved in jury of our sub-regional contest and offer problems and so on. So today, it's right, I didn't code it myself most of solutions, and yesterday I read solutions and so on. So maybe some details will be mystery for me, but I think that main ideas should be clear, and I hope you enjoyed the contest. You see, we have some specific in our sub-regional contest, that we have very wide range of teams, I mean skills, their skills, because we have teams from very typical universities from nearby regions, and they do not participate in ACM ICPC contests and do not have any experience in it. And because of it, we have a large set of very basic problems. But from the other hand, each year we have teams which can advance or already took part in World Finals. Sometimes they got medals in previous years. So usually our problem set contains easy and hard problems as well. And you see, it passed 4 or 5 years since sub-regional contest, but I think it was quite interesting and contained some interesting ideas. Okay, it's time to start. If any of you have a printed copy of statements, it will be good for me to have them. Thank you. And we start from maybe one of the hardest problem on this contest, problem A, coffee. The problem was about n groups of students given the size of each group. Each group contains at least 2 people, 2 students, and there is a restaurant with tables, and each table has seats around it, and you should distribute students and groups of students over the tables in such a way that each student has at least one another student from his group in his or her table. You can split groups. You can mix different groups around a table, but you should need to use as least number of tables as you can. Okay. The first idea here, it is easy to see that it is monotonic function. If it is okay for us to use, for example, X tables. So we can use binary search to find a boundary between false, false, false and the first yes, the first true. So all we need is to write a function, a Boolean function, to answer on the question if it is enough X tables to place all students around them. And this function is basically the main issue in this problem. Okay, I'll show you the solution of some participant, and I'll describe you main steps and main ideas around this solution. Oh, maybe I can reduce the font because it's easy to see. Do you see it well? Or should I enlarge the font? Is it okay? Enlarge. Okay. Actually, I understand you because my eyes are not good too, and I always do not see something. And larger, larger. Okay. Let's look at it. If you have a group, and this group contains odd number of students, it means that after you will split it, at least one group will have odd number of students. At least one part, at least one table will have odd number of students from this group. You see? And it is forbidden to have only one student. So this group, this part of group will contain at least 3 students. 3, 5, 7, etc. So you always can think that you divided the group like this, separating a triple, 3 people from it. And all other people, all other students from this group can be joined by pairs or by triples. And we can put them together or separately on different tables. Because if we have, for example, 7 people from this group around the table, we can think about it as 3 people plus 2 plus 2. You see? If we have, for example, even number of people around the table, we always can think about it as 2 plus 2 plus 2 plus 2 students and so on. Okay. So this part of solution calculates the minimal number of triples it will be. You see, if the size of group is odd number, so it should contain at least one triple. We increment the number of triples. And what is the maximal number of triples that we can have? The variable triples contains minimal number of triples. But for example, if we have something like group of 9 students, we can think about it as 3 plus 3 times 3 pairs, or 3 plus 2 triples. You see? So this variable is for maximal additional number of triples we can achieve. We use this tricky formula because, for example, if we have 4 students, we cannot separate triple from it, because if we do it, one student will left and it is forbidden. So we need to separate triples by, pairs. That's why it is divided by 6, but after it multiplied by 2. So this number, triples, is minimal number of triples we will have. And this number, extra triples, is the largest number of extra additional triples we could have. Okay. After it, if the size of table is less than 6, it means that a single table could contain at most 1 triple. You see? It's not enough for 2 triples. And number of triples is greater than number of tables, no solution. We cannot use X tables to find a place for each student. Okay. Another block of solution. The variable waste will contain the number of seats that we will not be able to use. I mean that the seats for sure will be empty. Do not look in this part for now, but the last line is the variable all is just the total number of all students. It is sum of all AI. And if the total number of all students is less or equal than the total number of seats minus the total number of seats which for sure will be free, will be vacant. It means that we have a solution. And our goal is to find the number of places, of seats, which for sure will be free. There are 2 main cases here. The first case, if a table contains odd number of seats around it. This case. If table is small, if table contains at most 5 seats, So, I'm sorry. This case is for even, right? The size of table is even number. Okay. And if table is small, is less than 6. But by the statements, the size of table is at least 3. So the only case left, it is R equals to 4. It means that we have triples, and for sure we should put them around some tables. And actually we need at least triples tables which will contain 3 persons from the same group. And in this case, each such table will have one empty place, one empty seat. And so the variable waste here is just the number of triples. Okay, another case. If tables are large enough, but they are even, they contain even number of seats around them. If we have odd number of triples, for sure at least one table will contain odd number of triples. And for sure at least one place will be empty. So in this case, the variable waste equals to 1. Another case. Okay. If table contains odd number of seats around it, let's calculate the maximal number of triples we could have. The maximal number of triples we could have is triples plus extra triples. And if this number is less than the number of tables, and each table is odd, so the rest tables which will not contain triples will always contain odd number of students, and one place in each of them for sure will be empty. So in this case, you can write here, I believe, just a sign. So in this case, you should find the total number of tables and subtract the number of triples and the number of extra triples. I mean, the greatest number, the largest number of triples we could have. Okay. But in other case, if total number of tables is less or equal to maximal number of triples we could have, we should compare their remainder modulo 2. Do they have equal remainder modulo 2 or different? And if they differ, it means that it will be one table which will contain for sure one empty place. I think we can do it in this way. So here we have calculated the number of seats which will be empty for sure. And just checking if we can fit all students on the left seats, we can answer on our main question. X tables, are they enough for students or not? And after it, you can do just binary search using this Boolean function to find the answer for the problem. Okay. Actually, I've read many solutions for this problem, and all of them are different. Because these cases you can find and consider them in different permutation, and you can find different cases, but the main idea that you can consider all of them. Okay. Next problem, right? The next problem is chess championship. This problem has different solutions, and also it has O n squared solution. But in these constraints, it was enough to implement n in power of 3 solution, because 500 is not large number. So, the second solution will be much easier to understand, to describe for you. So, and actually, I'm not sure I can remember right now squared solution, but you can find it. It uses some more tricky properties of this system and some combinatorics. But we will use to solve this problem just dynamic programming, and will be enough. Okay. I do not think we actually need it. The problem was about 2 teams. Each of them consists of n players, and you know skill of each player. So you have 2 sequences. The first sequence A, and the second sequence B. And as it is written in statement, all values 2 multiplied by n values are different. So, for example, you can renumerate these numbers to be, for example, from 1 to 2 multiplied by n. Or if you want, from 0 to 2 multiplied by n minus 1. Okay. And the problem was to find the number of ways to match first each player from first team to one player from the second team, and vice versa, in such a way that exactly x, k, that exactly in k pairs, the first team, the player from the first team has greater skill. Okay. For sure, it is very easy to find two values, x and y. The number of pairs in which the first team will win, and the number of pairs in which the second team will win. You know that the total number of pairs is n, and you know that x is greater by k over y. So all you need is just, for example, plus these two equations, and it's easy to see that if n and k have different remainders modulo 2, different parity, the answer is 0, because we do not have anyways. Okay, and we can easily find solution of this equation, two linear equations, and find x and y. Okay. What we do next? Let's assign a bracket. I mean round bracket, opening or closing, to each player. We will assign opening bracket to each player from the second team, and we will assign closing bracket, round bracket, to each player from the first team. And after it, so we have brackets. And after it, let's construct string containing 2n brackets, n opening and n closing, in such order each corresponds to the skills of these persons. I mean that we can make large array of 2n elements and sort it by skills. And for example, if A1 is 1, A2 is 5, A3 is 6, B1 2, B3 4, B2 4, and B3 is 7, then our sequence of brackets will have the form, will be closing, opening, it's A1, it's B1, opening, B2, closing, A2, closing, A3, and opening, B3. You see? We just ordered, use typical sort algorithm for all 2n elements. Okay, and in terms of this sequence of brackets, now we do not need any skills, because the order of brackets reflects the skills, the order of skills. Okay, and all we need now is to divide this sequence on pairs of brackets. You see? If I have a match, player number I from the first team versus player number J from the second team, I can find the corresponding bracket here corresponding for AI, the corresponding bracket for BJ, and I can pair them. And if this pair looks like this, opening bracket at first and closing bracket after it, it means that the team from the first team, the player from the first team has greater skill. And if my pair looks like this, it means that the player from first team has less skill than the player from the second team. Okay, so our goal now is to divide this sequence into pairs, that each pair contains two different brackets, and the number of brackets like this, number of pairs like this, is X. And the number of pairs in this order is Y. I mean that it could be some space between these brackets. They are not necessary one after another. And the same for this situation. Okay. So, to solve it, we can use dynamic programming. Let's go through our sequence from left to right. Sequence of brackets. And our current position is I. And we know the value Z, I, P, Q. It means that on prefix, on this prefix, for example, length of this prefix is I. We already assigned P pairs like this and Q pairs like this. And we know this value. And let's do dynamic programming, updating next states. So if we have such state, let's look into on the next bracket. For example, it is closing bracket. The situation, the case, if it is opening bracket, is the similar. Okay, it is closing bracket. What should we do? One option is not to assign this bracket to any other pair. And our new state will be Z, I plus 1, PQ, so we can just update the number of ways to get this state from this value, because we do not use this bracket at all. And another option, we can use this bracket, but we can use it if and only if there is some opening bracket here which wasn't used before. It is easy to check it because moving from left to right, we can maintain number of opening brackets, number of closing brackets, and if number of opening brackets is O, we can check this expression. It is a number of opening but not used brackets. And if it is positive number, we can use this bracket, we can pair this bracket with the sum of previous opening brackets that is unmatched for now. And for us it is no difference to which of bracket to match it, because it doesn't affect our future. So what state will it be? We increase the length, but we also increase the number of matchings like this. And the number of matchings like this is constant. It is cool. It doesn't change. And what number of ways we should add to this state? Can you help me? Who can? Now I am in state IPQ. And I have an option. I have an option to choose opening bracket for my closing bracket right now. And how many options I have? Yes, this number of options. So I need to multiply this number of options to the value in this state. And the case if the next character is opening bracket, it is completely the similar. So I have order cube states, and I can process one state in constant time, O of 1. So my solution works in cubic time, and also right now it uses the same memory. I'm not sure about will it fit into the memory, but you always can reduce the memory, storing only 2 layers for the matrix Z, because if you are processing layer I, it affects only the layer I plus 1, and so on. You need only 2 layers, previous and current and next, and you can swap them. Usually this trick is implemented by making this dimension of size 2 and using remainders over 2 accessing this dimension. I have solution, but maybe it's clear for now. Read, check parity, find A, B in our terms X and Y. No twice, because I match next next bracket with one of the previous.
You can call the same arrangement twice.
No, it will not count.
Yeah, I know, but how do I see that in the solution?
Because you have strict order of matching. Because you take next bracket and you match it. You do not do matchings inside previously processed brackets. You always take next bracket and look for its pair. You see? Okay. This part of solution is just to build bracket sequence, and we have right now bracket sequence. We have initialized dynamic programming. I think the array C is needed to store number of opening brackets and number of closing brackets on the prefix. For example, C of 0 or C of 1 will be our variable O. And let's go through the sequence of brackets from left to right. Current state, next state. We need to use remainders modulo 2 because we store only 2 layers in the array Z. We initialize the next array, the next layer with zeros, and iterate through all possible P and Q, but in this solution it is X and Y. Y. And if we have some reason to update our next state, because if the current value is 0, we do not have any reason to do it. We calculate the left number of opening and closing brackets on prefix. It is just this expression and the symmetric. This assignment reflects this line. We do not use a new bracket at all for now. Maybe it will be used later. And if we have opening bracket and we have at least one matching bracket, also, actually we do not need it because we will have multiplication by 0 here and nothing will change. We increment our next value. It is this, like this line, and the same. Okay. And we maintain the number of opening and closing brackets and just print answer. So this solution uses n² memory and cubic time. Any questions about it? Thank you. Next problem. Next problem, C, was about geometry. I'm not sure, but What topics Maxim has covered on the first week? Geometry? Not? Okay. And nobody of you, as I remember, solved this problem, right? Good work. I can use this board. Okay. The problem was about the system of ropes and one ball. We have horizontal surface, something like sail, and n ropes. And one ball, and this ball is attached to the end of each rope, and for each rope you know the coordinate. It starts on the sail, and you know the length of each rope. And the problem was about to one after another, we cut some ropes n-1 times, and ball after each cut can move to minimize its potential energy to make system stable again. For example, here, if we cut this rope, I believe that it will move to the down and to the right using some path and so on. And considering that the speed of ball is exactly 1 unit of distance per second, there were many requests in problem. What is the position of ball in specific times? And your task was to give responses for each request. Actually, the problem is about to simulate this system, to simulate how ball moves. And after you have found its complete path, you can easily give answers on requests. Okay, let's look into this system in details. Actually, if we have one rope, the possible positions of ball are half of one circle. If we have rope here of length L, L is the length of rope, so ball can be in any position in this half of circle. And if we have many ropes, so we should intersect all these halves of circles. It will be some interesting figure as a result, as intersection. And what point the ball will be? Yes, it will be. It will have the least y coordinate as it can, because any system, as you know, tries to minimize its potential energy. So if we have some halves of circles, I'm not good in drawing. I'll try again. For example, if we have such two ropes, the position of the possible positions of our ball, this figure, and the ball will be here. If we have, for example, this, the third rope, then possible positions have boundary of 3 arcs of circles, and it seems this point has least coordinate, I mean y. Okay. If we have current state of system, I mean we have current subset of ropes, because some ropes already, we cut some ropes already, we can find this figure, I mean arcs, and it is not as hard as it looks at first. In many geometrical problems, you can use approach called vertical decomposition. I think that I at first used this term in programming contests many years ago. You see, what are critical points in this system? I mean, critical points are this example is good. I can do something like this. Let's draw vertical line passing through each critical point, and all critical points are endpoints of circles on the sail. And actually I do not need all of them, but I need only such points that, you see, among all left endpoints I should choose rightmost, and among all right endpoints I should choose leftmost, because I'd like to find intersection, and intersection for sure will be in these boundaries. So I draw this vertical line, I draw this vertical line, this vertical line. I draw vertical line passing through each critical point, and critical points are endpoints of circles on the tail in range from left and right interesting points, and also all points of intersection of two circles. I just can intersect every circle with every another circle, each circle with every another circle, and find intersections and draw a vertical line through these points. Okay. And now I can solve problem to find this figure, this intersection on vertical stripes. Vertical stripe is part of plane between two neighboring vertical lines. And if I look on two neighboring vertical lines, it is not possible case that some arc crosses another arc between these lines, because this point would be critical, and we will have some vertical line between these, and they will not be neighboring. So if we look on a stripe, we can be sure that no two arcs intersect inside it. They can intersect on boundaries, but not inside. We have such arc, such arc, such arc, and so on. But we want to find intersection of halves of circles. So what arc will be the part of boundary of intersection? What arc should I choose here if I want to find intersection? Yes, highest. And it is very easy to find highest of them. I can, for example, just check check line between in the middle of this stripe and find corresponding y coordinate on each arc, and choose such arc that have greatest y coordinate. Okay, so it is very easy to find such representation. I can show you the code of it. There is some geometry stuff here. Point, circle, arc. You see arc here is a circle and two values of x, x1 and x2. It is boundaries, because in this problem we do not need arcs like these. All our arcs all points of our arcs have different y coordinates. So we can represent an arc using this method. Okay, find x. Find x is simple function to find y coordinate by x coordinate for a given circle. It is standard function intersect cycles. We intersect two cycles, and all we need to find is x coordinate of their intersection. And all our circles have centers on the same horizontal line, so intersections, two circles in general have two points of intersection. But in our case, both points will have the same x coordinate. And the method find arcs, it is exactly the method which I've covered before. Calculate L and R. It is maximal from left endpoints and minimum from right endpoints. Let's intersect all pairs of circles, and if x coordinate of intersection is inside L and R, we add it as critical point. Sort all critical x coordinates to find vertical lines. It is no problem that some stripes, for example, will have zero size, or for example, very small size. Just, it's no problem. We use, we skip them. You see? And we consider the stripe for between point I minus 1 and point I. The point between is just average of them. Let's go through all circles, and for each, not circles, but half of circles. And for each half of circle, find the corresponding y coordinate using find in x function. And we should find minimal value. I think minimal because in this solution, y axis goes from top to bottom. And we add this arc to the set of arcs, which represents our figure. Okay. It's good. And now, also we need method, we need function to find bottom point of such figure, to find the position, the final position of ball for given state of ropes. This function is find bottom. We have our intersection. Intersection is just sequence of arcs. And we iterate through all of them, and we find the value of this with greatest y value, because our y axis goes from top to bottom. Okay. And after it, we build the path of our ball. And it is very easy because what is our path? For example, it is our current state of ball and our figure, our current intersection, our next intersection, because we have cut some rope. For example, like this. It means that ball will throw down to this point, and its path will be a part of this arc, and so on. and it will finish movement in the bottom point. So it is very easy to write function find path. Function find path given next state, next intersection of halves of circles and two x positions. Two positions. It is coordinates x. The x coordinate of current state of ball and his target position here. And all we need is just move among arcs and crop these arcs are ignored, and arcs between these positions will be the part of answer. And so after this, we have complete path. We have complete path of our ball. This path consists of arcs. If it have this arc and next arc like this, it means that it flies down on this part of its path. So all we need after it is to process this path and to find position in this path taking in account current time from request. Okay. Any questions about this problem? It is not easy problem, but actually it is not problem like no team will solve it during the contest. Okay, it was problem C, and our next problem is problem D. Divide the kingdom. Divide the kingdom. It was the problem about graphs. You are given undirected tree, connected graph without cycles. It was Berland kingdom. And as it was written in statements, the king and the queen are going to divorce, and they want to split the kingdom. The king wants such part of tree that it is subtree. I mean, it is connected part of the tree. And also there are some requirements. The first requirement that the diameter of this part should be d1. It is the distance between points which are most far from each another. And the second requirement is if we count all such vertices which are on boundary of his kingdom. Boundary means that this vertex is a part of pair, such pair that the distance between these 2 points exactly d1. The number of such vertices should be not greater than c1. So 2 requirements, 3 at total. Subtree, diameter is d1, and number of vertices on boundary is c1. And the same thing, the similar thing should be for queen. She has d2 and c2 values. Also, their kingdoms should not be connected. We cannot have direct edge between their kingdoms. And all cities which are not from kingdom of king and queen, they should be destroyed. And we have a price, a cost to destroy a vertex. It is pi. And our goal is to find such 2 subtrees which meet the requirements of king and queen, that the total cost to destroy all other cities is minimal. Okay, not easy statement, it is rather long, but it has examples, it has two examples and picture, and so I think that it is understandable. Okay. Let's iterate through all candidates of cities which should be destroyed, and such cities that the city divides 2 kingdoms, kingdom of king and kingdom of queen. I mean that we can have outer loop over all vertices, and we can say, okay, I'll destroy vertex I. If I destroy single vertex, my tree in general will be not tree anymore, but it will be forest, a set of trees. These three, these three, these three, these three, and these three, and so on. And after it, what we need? We need to check each component and to check, can we make king kingdom in it, and we should check, can we make queen kingdom in it. And if answer is yes, we should find optimal positions of kingdoms in each component. And if for each component we can calculate 2 values, minimal number or minimal total cost cities to delete, that the rest vertices are king kingdom. I'll call it Kj. And Qj is just the same for queen. I take the component j, and I'm trying to find, I find optimal position of queen kingdom in it. So I find total minimal cost cities to destroy, that the rest cities form the queen kingdom. Okay. And I can do it, and if I can do it, if I can find such values, I can, for example, greedily choose two minimal values and use them, destroy all other values, and I can choose the best answer over all possible values I, and find the answer for this problem. We have n iterations here, and in total, it is easy to see, we will have n different components over all iterations of our main cycle, because each tree has n minus 1 edges. You see? The total number of edges in each tree is n minus 1. And if we destroy the vertex I, the number of components will be di, where d is degree of this vertex. But the total degree of all vertices is number of edges multiplied by 2. So in total we will have a linear number of components to process. And let's process each component and find the answer in it. Okay. There are two cases. D is even number or D is odd number. If D is even number, it means our diameter is even number. It means that the kingdom will have exactly one center. But if the value d is odd number, then it will be two centers connected by edge, and the picture will be something like this. You see? It is two different cases, but they can be solved very similarly. Okay, this case. For now, our problem is to process single component, and for given D and C, to find the best position for kingdom. Okay, we can try each vertex in this component as a candidate for the center. For example, if this vertex is candidate for the center, we can find the distance from it to any other vertex, and if distance is greater than D, the vertex should be for sure destroyed. If the distance is less than D, that we will not destroy this vertex for sure. But if distance equals to D, it depends on number of vertices having such value. Because if this number is less or equal than C, we shouldn't do nothing. But if we have this number of such vertices is greater than C, we should destroy some of them. And if we think what is the best idea how to destroy them, the first idea is very greedy, just to sort, for example, them by their price to destroy, and order, sort this sequence and destroy cities in this order. But it doesn't work, because you occasionally can reduce the diameter. For example, look into this example, and for example, the price for example, you need to destroy 4 cities, 4 vertices, but the price to destroy these 4 vertices is 1, and 100 is price to destroy these 2 vertices. And if we will use naive greedy method, we will destroy these vertices, and we will reduce the diameter. But we cannot do it. So we need to use some more tricky idea. And it is easy to see that actually each vertex is described not only by its price, its cost to destroy, but also it is described by the vertex which is neighboring to center and lays on path from center to this vertex. For example, for these and these vertices, this vertex is important. For these 2 vertices, this vertex is important, and so on. And what we need is to leave at least 2 important vertices that will have undestroyed vertices from the list. So our greedy method to do it is just do it, but we are not allowed to leave only 1 important vertex with undestroyed cities. And on each step we just destroy destroy the vertex with minimal cost, and this rule should be true. We cannot violate it. Okay. It is easy to see that if we look into the case when diameter is odd number, the situation is quite similar. Just we have 2 important vertices. We can think that our center actually is between them. And the total complexity of this solution is, in total we will have linear number of components. As you remember, in each component we need to try all possible vertices or edges as centers, and inside it we need to use something like BFS or DFS to find distances and so on, and to make to implement greedy approach. Maybe we need to sort something. Maybe we need n log n, where n is the size of component. So the upper bound of running time of this solution is n in power 3 multiplied by log n. Actually, we have small numbers as costs, and maybe we can use some linear sort algorithms to reduce the complexity. Any questions about it? Okay. I think it's a good idea to have 5 minutes break, and we will continue after it. Thank you. You can call your friends if they are outside. Okay, take your seats and let's continue. I've counted my t-shirts and found that I have at least 3 t-shirts. And I decided to make one more rating in our group. And this rating will contain only contests which I will host. So the contests of the second week. And according to the results of these contests, and also I can remind you that the rating counts not only your official participations, but also it counts your, if you solve problems after the contest. And according to this rating, I will give T-shirts to the best 3 students from you who is here, because I've heard that some students are absent and take part remotely. Okay? So wish you luck, and if you are not from the very top, you can find strengths inside you and make it, do it. Okay. Problem E, dragons and princesses. It was not hard problem. It was about prince and dragons, princesses. It was checked stripe, linear stripe, and there was prince moving from left to right, no step backward. And his favorite, his dream princess was in the last cell. And each other cell contains dragon or other princess. D stands for dragon, P stands for regular princess, not his dream. And each dragon has gold, GI, number of gold coins. And if prince goes through the cell with dragon, he can kill it and take gold coins, or he can pass the cell without gold and without killing dragon. And if there is a princess, each regular princess and the last princess as well has requirement, I do not remember, R, are I. And it means that if prince killed at least or more, I do not remember. At least are I dragons, he married and finished his trip. But actually, our prince wants to marry on his dream princess, the last princess. So that's why sometimes he do not want to kill a dragon, because if he kills dragon, the number of killed dragon increases, and he will marry before the target cell. Okay. And the problem was to find the way for prince to marry on his dream princess. And if there are many ways to do it, he wants to bring as many gold coins as he can. Okay. Let's solve the problem, and I think it's just better not to kill dragons, but catch them and put them in bag. You can think about it like a prince has a bag full of dragons. Initially it is empty, and he goes from left to right. He see dragon, and if he see dragon, he take his money without any questions. Take dragon and put in his bag, and so on. And he will do it with no options. Just see dragon, take it, take his money, and he goes, and he meets first princess, and this first princess tells him, if you have at least I dragons, marry on me. But this prince doesn't want to marry. So what he can do? He can put some dragons from his bag back, return them on his places. And what dragons he will return? Yes, he could use greedy approach here. Just dragons having the smallest number of golden coins. And how many dragons he will return? He will return such number of dragons that his bag will contain strictly less number of dragons than are I. So here you can use just simple priority queue, or for example standard ordered set, STD set in C++ to maintain all dragons. And if we have, and this priority queue or STD set, it is a representation of his bag. And if he meets princess, and the requirement of princess is less or equal than the size of priority, than the size of his bag, he will return some dragons back and with money, with their money, using greedy approach. And he will go through all princesses from left to right, left to right, left to right, and the only issue that after finishing his way, he can have less number of dragons in his bag than his dream princess wants. So it means that this story doesn't have happy end. No marriage at the end in this case. But if he has at the end the size of bag greater or equal than the requirement of his dream princess, it is the solution. Okay, so the solution is just simple, no segment trees, no difficult data structures and so on. Just priority queue and go from left to right. Any other questions? Okay. So. Another greedy problem, dumbbells. Problem F. The problem F was about to make sets from some items. These items were characterized by two values, weight, MI, and price, cost. Yes, and cost, CI. Also, we have n items, and also we have special number k. It means that each set should have k items with distinct weights. And also, if we look in each set, the weights in each set should be equal as sets, you know. Okay. It was easy problem, and I think most teams have solved it. For each weight, for example, using array or map, we can calculate number of items of such weight, and also it's good for each weight to make a list of items of such weight. Okay, after it, for sure, we are interested. Our goal was to make as many sets as we can to maximize the number of sets, as I remember. And if there are many solutions, we should find solution with maximal total cost or minimal total cost. I do not remember. So, because we want to maximize that number of sets, we are interested not in all weights, but we are interested in k best weights. We can order all weights by number of items having this weight, and if we order them, the weight on position k will have x items of such weight. It means, you see, it doesn't mean that, for example, this weight we should take for sure. Because, for example, next weight here can have the same number of items. X, also X. And these also X. But next, for example, X minus 1. It means that we are interested in such a prefix of weights after sorting. Each of them, we for sure will take all weights from this prefix. Okay. And the number of sets we will find will be exactly the x. It is exactly the number of items which corresponds to the weight on the position k after sorting by number of items from greater value to least value. Okay. If we look into each weight, we do not need all items from this weight, right? Now we understand that we need only X items from each weight. And how can we choose these items? Just use greedy approach again. For each weight, we can order all items having this weight and choose X best items, best by cost. And after it, for each candidate of weights, we have value the sum of X best costs in it. And from these candidates, we can have more than K candidates. We should choose K best candidates. And again, we use greedy approach to choose best K weights having better values. Okay. Problem F. Problem E. It was solution for problem E. Okay. So this problem is very, very, very greedy. You should use greedy approach 3 times, I believe. And the constraints for these problems are not high, and it was allowed to use just simple sortings to find some values and so on. Okay. Do you have any questions about it? Can you raise a hand if you solved problem F on the contest? Many of you. Thank you. Problem G, database optimization. This problem has a real-world statement about database, about queries, and so on. It is about n objects, and each object has at most 4 properties. Each property has value, so each object has at most 4 equations like this. And also we have many requests. We have M requests. Each request is some kind of typical SQL request to find number of objects which satisfy given condition, and condition has the form property 1 equals value 1 and property 2 equals value 2 and so on, but the number of such terms at most 4. And the problem was to simulate database and to give responses for each request. Okay, if we use some naive approach, it will be something like n multiplied by m. For each request, we can iterate through all objects and check does it satisfy conditions or not. And if it satisfies conditions, we can increase the answer by 1 and so on. And it will be n multiplied by m solution and time limit on test 10, for example. Okay, but it is very often situation that the statement contains some note how to solve the problem, and this statement, in this statement, it was number 4. It is very small number, and if we have such small number in statements, we should use it. Okay, and let's use it in this way. Let's take an object. As an example, I will use object with 3 properties, but we have at most 4 properties, but it's better to explain the solution in smaller example. For example, property A equals 1, property B equals 7, and property C equals 3. If we have such object I, we can easily find all requests, such requests that this item is a part of answer for this request. For example, we have only in this case 7 requests here that this item is interesting for request. It is request like first request having the only condition A equals 1, the only condition B equals 1, the only condition C equals 3, 2 conditions A equals 1 and B equals 7, 5 A equals 1 and C equals 3, 6 A B equals 7 and C equals 3, and the last conditions are all the complete condition to match the item A equals 1 and B equals 7 and C equals 3. So there are only 7 requests which take in account this item. So we can take item, iterate through all possible subsets of its properties, and for each subset of properties we can add 1 as a result. And if we process in this way all items, for each item we will do at most, we will consider at most 15 queries, because it is 2 in power 4 minus 1. Minus 1 because empty set of properties, of conditions is forbidden. And add 1 to each query. So we can pre-calculate for each query the answer. And after processing all items, we just read the request and get pre-calculated answer. If no answer, then print 0, and so on. So the complexity of this solution is 15 multiplied by n, maybe you need some large constant, because, for example, in my solution I used something like map from vector of strings to int. It was cache for request vector of strings. It was ordered vector of conditions. So each vector here contains at most 4 elements. So, and after it you read request after request and look into pre-calculated map to find if you have answer for it or not. If no answer, you can return 0. You can just use map, because map will create 0 as default value and use it. Okay. Do you have any questions here? It was problem G. I have some sample solution for it. I do not know is it good or not. Just read number of objects. It is for pre-calculation, as I wrote on the blackboard. Read properties of object, sort properties before processing them, look through all possible subsets of properties, and for each subset increment the result by 1, and after it process all requests and get result from pre-calculations. Okay. The next problem was about pearls, Sultan's pearls. There were in total n pearls, and m of them were hanging, and the rest n minus m are on the table, and each pearl is characterized by 2 values, its weight and price, I believe, and the state is stable if the total weight of table pearls multiplied by k is given in the input, is greater or equal than total weight of hanging pearls. In this case, the state is stable, and initially I believe it was given stable state, and we need to help somebody who want to get some pearls from it, and he wants to get as many, he wants to receive as many money in total as he can, and each time he removes 1 pearl from right end, from hanging end, or from table. If he removes pearl from the table, actually nothing changed, just Perl is removed, and this inequation should be held again. It is not allowed to have unstable system. But if he removes the Perl from the hanging end, he should turn Perls in such a way that this hanging part contains exactly M Perls. And somebody wants to rob one Perl after another, to rob one Perl after another, and to get as much money as he can. Okay, it's easy to see that the Perls which will be removed is some prefix of all Perls and some suffix of Perls. And it is easy to see that if we know these prefix and suffix, we can always do our steps in specific order. I think that we can at first try to move all hanging, to remove all hanging Perls, and only after we removed all of them, we can try to, we can remove all Perls from the table. So we have two types of moves, and we always can do at first moves to remove hanging Perls, and only after them we can do moves to remove table Perls. It's easy to see that if we do our actions in this order, it will be more safe than any other order. We always can do it. Okay, it means that we can go through all possible values, how many Perls from right end we will remove. For example, if we know that we want to remove I Perls from right end, it is easy to see that value j, number of Perls which we can remove from the left end, is monotonic function again. If we remove I Perls from right end, we can remove 0, 1, 2, 3 persons from table, but we cannot remove, for example, 4. And for sure we can't remove 5, 6, and so on. So we can use binary search here to find for specific value I, find the maximal such j that the situation is stable. So the solution is just go through all possible values of I from 0 and next, and for each value of I using binary search you should find maximal possible value j, and you will get a candidate to answer, and among all possible candidates we will choose the best. It is problem H. And for sure to make calculations faster, we need some fast way to calculate the sum of costs and sum of weights on prefixes and suffixes, and we can easily do it using trick called partial sums. If you have some array, say A1, A2, A3, A4, AN, you can calculate new array for example, SA, and SA 0 is 0, SA indexed by 1 is just A1, SA indexed by 2 is the sum of first two values, and so on. It is partial sums. And so on. And if you need to find the sum on some segment on array A, for example, from L to R, all you need is just find the result of expression SA R minus SA L minus 1. And it is an easy trick to pre-process the array to find sums on some segments in it. And here we will use this trick. So the solution is, oh no, it is not written by me, but nothing difficult. Okay, let's read pearls, and at the same time let's calculate partial sums for weights and for costs. I think that here I is the total number of pearls that will be in answer. It is different from my explanation, but almost it's the same, because if we have I pearls left, the last M pearls will be hanging pearls, and the previous and I minus M pearls will be at the table. And here we will use binary search to find value L. And value L here is our J. It is just the maximal number of pearls that can be removed from the table. And we just check, should we update the answer to the problem? Does found answer better than previously found answer? And if yes, we can update it and print the results. Okay. Problem I. Problem I wasn't solved by any team from our camp, but when I used this problem set for other teams, maybe sometimes this problem was the next which was solved by teams after 8 problems, after the best result of these teams. Okay. This problem was about NIM game, and all you need about NIM to solve this problem was NIM game is game when you have piles of some items, stones or maybe something else. And Actually, I forgot the rules. What are the possible moves for player here? A player can take take any number, take any number of stones from it, right? Yes, sure. So the game is there are n piles. Each pile contains some number of stones. You know the number of stones, ai number of stones in pile I, and on turn, a player chooses a pile and removes some positive number of stones from it. And if a player cannot make a move, he loses. It is a very famous game, and I will not stop on it in details, but it is well-known fact that this game is that the first player will lose if and only if you XOR all values of A and result is 0. I mean this symbol as bitwise operation excluding OR, XOR, XOR. Okay. And this problem was about this game. It was given the sequence A, and it was asked about how many such values x exist, that if you do calculations, if you before game remove x stones from each pile, the state will be bad for the first player. You see, the motivation was that the second player wants to cheat, wants to remove x stones from each pile before the game in such a way that he will win it in game. And the question is how many such values x exist. The constraint so were very high, so we need to find some efficient solution to solve this problem. Okay. At first, if we are speaking about binary representation of integers and so on, we will think about values a as binary numbers, and we will use fixed widths. For example, we will add extra leading zeros to some of them to make all of them have the same number of digits, same number of zeros and ones. So we have, and let's print them as a table, one number per row. It's just random stuff. I'm not sure it is very representative. And after it, for example, we can easily check if x equals to 0 is good for us. Just count the number of ones in each column if number of ones is even number in each column, then x is good for us. And then x equals 0 is good for us. Okay. And for example, if looking on the last column, we can calculate the number of ones in last column. If this number of ones is even number, it means that x for sure should be even number 2. We cannot have 1 in last position in x because x. Oh, no, we can't have it. It's not correct. Okay. If another idea, let's calculate the number. Let's find the number of ones in last column, like here. And if it is odd number, it means that we cannot have even x. Because if we have even x, we have 0 in last position as last bit in x, and last column will be unchanged, even if we subtract x from each number. And the last column will not change, but in this case, last column has odd number of ones. It will not change, and in total, in last column, we will not have even number of ones, and we will not have 0 in total. So, for example, in this case, it is easy to see that x in its binary representation cannot have 0 here. But if x has 1 here, it will make some changes in our sequence. Let's look on changes. At first, all zeros will become ones. All ones will become zeros, right? Because we subtract x from each value. Also, for each 0 value, after we subtract it, we should remember that we should subtract 1 in next position, because 0 minus 1, and we have remainder right. Okay. So on next step, our state is that let's look on step I. It means that we are looking on column I, and we already have processed all right columns. And in all right columns, we left situation that number of ones in each column became even number. And here in this column, we are here in this column, and in some subset of rows, we already have minus 1 in our mind, because because previous calculations. You see? So right now, without any tricky observations, we have very bad state, because it is very large. The state is I, and subset of rows. But if we know that number of rows that should be reduced by 1 at column I is, for example, j, do we actually need to store subset, or we can find these numbers uniquely by some algorithm? Yes?
Sorry, what is J again?
J is number of rows, such rows that we should do -1 in these positions because previous calculations. You see, for example, when we looked at rightmost column and we decided to use 1 in our x at right position, it affects the number in such way that all ones change it to zeros, all zeros change it to ones, but we should remember that we have -1 for these and this position because of previous calculations. And here our state is, we are looking on column I, and we have exactly j rows from which we should subtract 1 because of previous calculations. And my question is, do we actually need to store subset of rows? Or we can find such rows using some method?
No, and you only need j model. I think you don't need, you only need j model 2.
We can find it because if x is equal for each number, and if for some number we have -1 in this position and some we do not have, we have -1 in such numbers that these parts are less. If these parts are small numbers and we subtracted x from them, we have -1. If this part is large number, we will not have -1 because of previous calculations. And we can just sort all rows by these endings.
What do you mean by large? You mean larger than x?
Yes, yes, yes. We can sort these rows by endings and take in account first j of them. And we can for sure say that first j of them will have -1 because of previous calculations, and the rest of them will not have. We do not have x in our arms. It is hidden, and some kind of this number j is some kind of representation of x. We do not know x. So the state of dynamic programming is the column I we are processing and the number of rows from which we should subtract 1 because of previous calculations. And we should not store which rows for which rows we need to do it. We can just use sorting to find them. And we need to use sorting by ending. We can maintain the order of rows, such order that they are ordered by this value. Okay, let's look into solution. Actually, all the solution, oh, it is a solution. I didn't write it. I do not prefer to write many operators in one line. So I'll change a little. Okay. So the array for our dynamic programming is number of bits multiplied by maximal number of numbers, number of rows. Initially, and this array stores the number of ways to get this state. For example, the answer on the problem nearly equals to dp 60. We have to subtract 1 sometimes because our calculations naturally use smallest value of a as possible value of x. But by problem statement, we cannot use x equals to smallest value of a. X should be less than any value of a. And because of it, sometimes we should subtract 1 from the answer because dynamic programming will find at least other, will not use this constraint. Okay. Let's read A. It is it uses 1 base indices. And let's go through right to left by columns. We will start from the column 0. Here C1 is the number of ones in column I. You see? It is just number of ones. If number of ones is even, we can just use 0 in x in this position. If column contains even number of ones, we can say, we use 0 in x, and it means, and we now consider that we do not have any modifications, any subtractions that we need to do because of previous calculations. We have j equals to 0 here. If we have j equals to 0, it means that the column is unchanged. And we can just do in dynamic programming this increment just because x can have 0 in this position. And the similar thing. If we have even number of ones, we can use 1 as bit in x in this position. This 1, it is just like the situation when we saw the rightmost column in our example here. we have even number of zeros. Yes. N minus C1 is number of zeros. And it is even number of zeros. If we have even number of zeros, we can try to use 1 in x. If we use 1 in x, our ones will become zeros, and our zeros become ones, and on next step we will have subtractions because of previous calculations, minus ones. How many it will be? It will be exactly the same number as number of zeros. Okay. And now we are thinking about options when cases when j is positive. So we have j number of minus ones, j number of minus ones in column I. And we know that we maintain the property that rows are ordered by their endings, so we can look just into the first j rows, and only them will have minus 1. Let's look in them. Because of if this number had 1 in binary representation in the position I, because of minus, this 1 is disappeared. That's why we have this line to maintain C1, actual number of ones. And else, if number, we are planning to do minus 1 for it. If number in position I has 0, this 0 became 1, so the increased number, C1, number of ones. And also we remember that in future, for sure, we will have one additional minus 1. And x is a variable to maintain the number of minus 1s, additional minus 1s in right column, in next column. Okay. And all we need is just 2 updates. They are exactly the similar. If number of ones now is even number, we can use 0 in x in this position. And it means that our next state will be, I've highlighted it. And we should increase the value by our current number of ways. And the opposite way, the opposite case. If actual number of zeros in this case is even, we can try to use 1 in positions here. In position I in x. So our next state will be next column, and number of minus 1s in next column will be nx because they are additional, and n minus c1 because of these zeros. We subtracted 1 from this number of zeros. It is our new state. And this state should be updated, should be increased by the current number of ways. And the rest code is just sorting. We are finishing to process another column, and we should resort rows using these columns. They were sorted, you see, by this ending, but we should sort them by larger ending. All we need is to make something like stable sort by these bits. Just split all rows on two groups which have 1 in position I, which have 0 in position I, and compose new order. You should write at first those who has 0 in the position I, and after it 1 in the position I. And just print the result, and as I told before, we should use the requirement from the statement that x is less than any value of a. But in our dynamic programming solution, it can be equal. So we should do -1 in some cases. Okay. And the complexity of this solution is, you can see, just number of the length of a, n, multiplied by 60. Because each state we process in constant time. It is not easy problem on dynamic programming, but I think it is quite interesting and useful. Okay. The next problem is very, very easy. Ternary password. Problem J. Someone had password. You are given the password. For example, 0, 1, 2, 0, 2, 2. It contains only zeros, ones, and twos. Don't use such passwords. And there was a requirement for the password that it should have exactly 1, 0, and exactly 3 ones, and all other characters should be 2. And we want to change the smallest number of characters here to meet the requirements. We can do it in greedy way, just to see if we have, for example, more zeros than we need to replace 0 to 1 or to value 2. But if we have less number of ones than we need, it is always good for us to replace 0 on 1. It means that if we can, by one change, to make situation better in 2 requirements, it is better for us. For example, here we need to have exactly 1 0 value and exactly 3 1 value. So we can take this 0 and we are planning to change it on 1 or on 2. And it is good for us to change it for 1 because we will increase number of ones and we will be closer for our requirements. After first change, we will have situation like this. And after it, this requirement is met, and this requirement is not, but for sure we can take, for example, any value equals to value 2, to digit 2, and replace it with 1. So we can use some very greedy approach here, just to replace one character to another if we need it, and our goal is to be closer in two requirements at the same time if we can do such change. The problem K. We have some time on it. The problem K was an interactive problem, and it was about trees. It was given a tree, and your task was to process n-1 requests. Each request is to delete one edge. For sure, after the first request, it will not be tree, it will be set of trees. And on each move, you take one tree, remove edge from it, and the number of trees increases by 1. And there are weights on edges, and then you remove an edge of specific weight. It will be two components here, and the weights of edges in these two components will be changed according to the following rules. In smaller component, all weights are multiplied by Wi. It is written in statements. If you delete this h, it will be two components. Look at the smallest component and multiply all edges in it by the weight of removed edge. And for another component, for bigger component, you should add Wi to each weight of edge. So each removal changes weights in two components that appear after removal. Okay, and you should simulate it, I believe, and in online mode. You cannot read all requests before processing them. You should read request and process it. Read another request and process it again, and so on. Okay, let's do it. If we are removing the edge, it is very interesting for us to find smallest component and to find bigger component. And it's not, but you cannot make, for example, BFS or DFS in this component or this component, because you do BFS, but this component can be large. And on one step, it should take you about O of n steps to find the size of this component, if you're unlucky. And as you need to process n requests in total, it will lead to n squared solution, and it is very slow. We need some faster method to find smaller component in online. And this method is as follows. Just let's do two BFSs, breadth first searches. At the same time, from this vertex and this vertex. And we just removed edge between them. And we will do them at the same time, step by step. Step of BFS for U, step of BFS for V, step by step of BFS for U, for V, for U, for V, and so on. Each step should be processed in constant time. And we will terminate this process, we will break this process when we will find that some BFS stops because it traverses the whole subgraph. So you see that in this case, if one component has size A and another component has size B, we need number of operations is minimum between them. Because after such number of operations, one of our searches will finish for sure. So making parallel two searches, we can locate the smallest component. And it will take for us such number of operations. And it is easy to see that in total it will be linear time of operations over all the tree, because each time you should add smallest part to the answer. And the worst case for us if this edge breaks the tree on two equal parts, and it will be something like n or n log n. Okay, and I think they are very close to this solution, because right now we can maintain for each vertex the index of component it belongs. We have some in some general state, we have some number of components, and let's maintain for each vertex the index of component of its component. For example, this component is 0, this component is 1, this component is 2, and so on. Also, for each component, we will maintain single number, say delta I. It is the summary increment for all weights of edges in this component. We will not do for bigger component. We need to add the weight of this edge to each edge, but we will not do it one by one. We can just store one single value for component, how large we should increase all weights in these components. I mean weights of edges. Okay, and let's process the query. It is very simple. We have edge. We can easily find the component it belongs. We can find easily the weight of this edge. It is just weight as written on edge plus delta from this component. And let's remove this edge. Find smallest component and make new component. Just renew the index of component for all vertices of the smallest component. And do it again and again and so on. For smallest component, we will multiply the weight of edges y by 1. It is small number of operations, the same. And for larger component, we just add the weight of our currently deleted edge to the delta. I think 3 or 4 teams solved this problem. Do you use the same approach or something the same? Okay. And the last problem was just easy to simulate the process. It was about 2 jury members. One jury member writes solution in T1 seconds, and another jury member writes solution in T2 seconds. All of them wants to write exactly in total n solutions, and they just start to write solution if previously was written less than n solutions, and we should simulate the process. And the most easy trick to implement this solution is to store, to maintain for each jury member the first moment, then it will be free again, that it will finish his current solution. Initially, for both of them, we have x0, x1 equals to 0. They are both have a rest at the moment 0. And look, after it, each time we choose the smallest number from x0 and x1 and analyze the situation. Should we give one more problem to this jury member or not? There will be case of there will be 2 cases, if x0 equals to x1 or not. If they are different, we just compare the number of previously written solutions with n, and if they did not write n solutions, we gave another solution to jury members, say x0, x0 increase by number of seconds he needs to write solution, and continue continue simulation. And if x0 and x1 are equal, then we should consider them at the same time. Just look to the number of previously written solutions, and they will both write new solution if they didn't finish, or they will end their process, and we will queue it from the program if both of them if they have enough solutions, enough written solutions. Okay, I think it was the easiest problem here. Maybe the second, I don't know. Any questions? No questions. And it's time to finish, right? Great. Thank you very much. I hope you will enjoy today's contest. And tomorrow I'm planning to have not so long discussion of solutions. And I hope that tomorrow I'll give you some more new topics. And it will be interesting for everybody. Thank you.